Proof by contradiction. Watch the previous video on proof by contradiction to show that root 2 is irrational. It's in a bit more detail than this video. So we start off by assuming that root 3 is rational. So we're contradicting this statement. So we write root 3 as a fraction where a and b are integers with no common factors. We square both sides, rearrange to make a squared the subject, and we see that a squared is a multiple of 3. If a squared is a multiple of 3, that means a is a multiple of 3, and we can write a multiple of 3 like this. So I've replaced the a here with 3n to get this. Expand the brackets, divide both sides by 3, so now we see that b squared is a multiple of 3. If b squared is a multiple of 3, that means b is also a multiple of 3. So now we have shown that a and b are both multiples of 3. If they are multiples of 3, then in this fraction a and b have common factors, but we said earlier that a and b are integers with no common factors. So there is a contradiction with what we said earlier, that there were no common factors here, which means that root 3 is irrational. Root 3 is irrational. Our assumption that root 3 is rational was wrong. Okay, now applying the same proof for root 5. So we need to show that root 5 is irrational, so we start off with a statement that contradicts this. So we're saying root 5 is rational. We write root 5 as a fraction where a and b are integers with no common factors. We square both sides, and then we make a squared the subject, so a squared is a multiple of 5. So if a squared is a multiple of 5, that means a is a multiple of 5. So a can be written as 5n. So now I'm going to replace the a with 5n like this. So we expand the brackets, gives 25n squared, divide by 5 on both sides, and now we see that b squared is a multiple of 5. If b squared is a multiple of 5, then b is a multiple of 5. And we already have this, that a is a multiple of 5. We said earlier that root 5 was equal to a over b, where a and b are integers with no common factors. But we've just stated that a and b are both multiples of 5, so 5 is a common factor to both a and b. So this contradicts the earlier statement. So we have a contradiction which shows us that root 5 is irrational. So this assumption that root 5 is rational is wrong. Okay, so we have two integers and they multiply together and the answer is even. So yes, you could multiply two integers and get an odd value as well for the answer. We're not looking at that case. We're specifically looking at the case where the product of these two integers is even. And if it's even, then at least one of these two values must be even to begin with. So either p is even, or q is even, or they're both even. So to do the proof by contradiction, we're going to go against all of this here, that at least one of them is even. What we'll say is that yes, if PQ is even, you could get an even product even if they were both odd. That's the contradiction we're going to start with, that they are both odd, and if you multiply them we'll get something even. So we start off with P is odd, that's an odd number, Q is odd. Use different letters. We're not saying that they're both the same odd number. If I use K there and I use K here as well, then I'm assuming that P and Q are the same. There's nothing in the question to suggest that they're the same. Okay, so I'm multiplying those two together, expand the brackets, do a bit of factorization, and what you've got here is a multiple of 2, so 2 times some terms here, so that's definitely even, this part, but then when you add 1 it makes it odd. But we were showing that it was going to be even. It's not worked out. So this is contradicting that PQ is even. So my assumption, which was here, that they are both odd, is wrong, which means that at least one of P and Q is even. This is true, this is wrong.